Greetings, everybody. I want to make a different kind of video here where I'll combine my transforming data guide with the R script that will help you transform variables if you need to do that at any point. So I just want to put it all in one video to make it easier and definitely go through these things on your own. I think it's all pretty readable, so I actually don't think you really need much of a video for this, but I'll just say a few things to hopefully be helpful, and we'll quickly go through this here. So the whole point of this is when we encounter scatter plots that show a potentially curved relationship between my explanatory variable and my response variable. You know, ideally, we've been seeing very clearly linear relationships, but sometimes it's not that clear. Sometimes it's curved, and we need to know how to work with that if it's curved. And this is where multiple regression starts to come in to help us with that. So here's a little guide to help you think about, this is very very procedural, to help you think about what kind of transformation you might need to do to your data in order to get in a sense, a linear looking relationship back between your explanatory variable and your response variable. And the point is, remember, when we want to model our response variable, we want that response variable to be described by our model, to be described by an explanatory variable. And it may not be a linear relationship. It might be a logarithmic. It might be squared. It might be cubed. It might be curved in some way. We are still doing linear regression because the slope coefficients, our betas, those are still linear. Those are just linear numbers. But we can do any kind of adjustment to x that we want or y to show a curved relationship between our variables. So here's a little procedural guide for how we think about this. Just focusing here on the left, this thing I have here is called the ladder of powers. And all it is showing us how we can put different exponents or do different things to a variable, x, y, price, square feet, age, and whether or not that is considered going up or down the quote-unquote ladder. Now, what does this mean? So whenever we have a generic variable or a generic equation, we are always having our variables to the first power. Y equals beta 0 plus beta 1x. Each of those variables is to the first power. This is where we always start. If we need to transform our data by going quote-unquote up the ladder of powers, then we go up in the exponent. So we can try an x squared. We can try an x cubed. If instead, based on the type of curve we're seeing, we need to go down the powers, we can, between 1 and 0, we can do, say, a square root, x to the 0.5, or y to the 0.5, price to the 0.5, square, feet to the 0.5, whatever variable you want. So we can go to a square root. After that, we can go even farther down the ladder and use what is the most common transformation, and that's to take a logarithm. We tend to take the natural logarithm, which, to avoid getting into all the math because it's not going to matter much for this class, just means a logarithm that is undone with e or the exponent. Excuse me, with e or the exponential. Whew, had something in my throat there. In any event, when we take log in R, it automatically does a natural logarithm, as you'll see. So Going down the ladder of powers means we can do a decimal like 0.5 or 0.75. We can then go to the logarithm, and we can go even farther and do negative exponents, -1, -2, etc. So up just means increasing the exponent, down just means decreasing the exponent or taking the logarithm. And that will give us different kinds of relationships between our variables. Now you might say, how am I going to know when to use this and where to use this? This is where this guide comes in. Each of these 4 segments shows us 4 possible types of curvature that we can see. So just focus on one region at a time. And that's what I have down below here, is one region at a time. So if I'm in this region 1 in my data, let's say these dots are some fake data here, then they are approximately followed by this curve, this part of the circle here. What I say then is, to fit data that look like this type of curvature, I apply an up transformation in X or an up transformation in Y. Either one will fit this type of shape. If we look in region 2 over here, let's say I have a shape that looks like this section with some fake data around it. Now, to fit this relationship, I can use an X that is transformed down, like a logarithm, or I can go up in Y, like a square. In this third region, if I have data that look like this type of curve, I can go down in X or Y. So I could take the log of X or I could take the log of Y. And that would fit this curve between my variables. Lastly, in this fourth region, if I have data that look like this, I can go up the power in X or I can go down the powers in Y. And you might start to recognize what some of these curves on their own might look like. Like this might look like a parabola to you, y equals x squared. You don't need to be responsible for mathematical functions, but I just want to point out that that's what you can do, is think about them that way. And I should be clear that you may not need to transform your data at all this semester, but if you do, like for that homework problem on 9C, these are some things you can start to think about. So I go through each region with some fake data and some example models you can use that take advantage of this ladder of powers. Just briefly, in this first region, here's what looks like my first region up here with some fake data that I generated. Since we can go up in X or up in Y, for example, we could do a model that's y is equal to x plus x squared. As a general rule, when we add powers to our model for our data transformation, we never take away the original variable. We just add to it. There are reasons to do it this way, and there are reasons to just add the x squared on its own and ignore the x. But for the purposes of this class, just think about adding on whatever the extra power is. Or we could, for going up in y, we could just make this y squared. For interpretation purposes, it's much easier to try to interpret my coefficients if I just have a square term over here. Instead of having a y squared and having to take the square root of everything to make this in terms of y. There's a lot of mathy stuff going on here. So you are probably not going to actually have to interpret any models like this. It's unlikely going forward. But I want to give you all these tools in case you do. So I have a separate guide for interpreting this type of information, and that will come along after this. But for now, these are just some example models you can try to fit. And again, I recommend if you're just going to do some powers, just add it on the x side because it's a lot easier and it keeps these coefficients separate than doing a square over here. And then if you want to put everything in terms of y, you have to take a square root of this side. So anyway, looking at the second region, so region 2, I have this upward curvature here, which looks like right here. I can go down in x or up in y. So if I want to go up in y, it's just like in region 1. But like I said, that becomes difficult to interpret. So a common thing to do is you can add, say, a square root term. And again, I'm adding an exponential term. And so for statistical practice purposes, we don't get rid of this linear x. We keep it there. And we just add on the square root, and we have particular interpretations for our coefficients. Or I just take the natural logarithm of x. And that has particular interpretations, which will all be in my separate interpretations guide. So this is an example of how you might graph and handle this kind of data. In the third region, coming down here, we have this type of curve. We can go down the ladder of power in x or y. So we can add a square root on the x side, or I can take the square root of the y side. Alternatively, I could take a natural logarithm of x, or I could take a natural logarithm of y. Either of those cases gives me downward in x or downward in y in terms of the ladder of powers. The convention when we need to go down in y is to take the natural log of y. I recommend this before anything else when you need to go down in y. This is very conventional. This is used the most commonly, and there are pretty well-defined interpretations for our coefficients once we apply that kind of transformation. So if you ever have data that look like this, I recommend taking the natural log of y and making that model. And finally, my fourth region, which looks like this curving upward again. We can go up in x, or again, we can go down in y. And I'm going to skip right to the punchline. Since we can go down in y, I strongly recommend just take the natural logarithm of y. It is straightforward, as you'll see in my interpretation guide later on. You won't need to do any of these things for a couple weeks, if at all, depending on how your homework 2 goes, as you'll see. But all the tools are here that as you encounter more complicated looking data, what you might need to do to fit. And the models get more complicated than this. These are just some examples for how you might start to model this curvature. You can try all kinds of things. We can try cubics. We can try to the 4th power. We can try negative powers, all sorts of stuff. But for now, just getting a basic handle on curved data, you can think about going up or down our ladder of powers and trying squares and logarithms. Occasionally a square root, but really logarithms are very interpretable in statistics, and so if you have curved data that needs to go down in y, just take the log of y. And lastly, what do we do with outliers? Well, we evaluate them. Sometimes it's data entry error, and we can omit them. If there's a special theoretical case, like if it's a house near a lake among a housing data set, then we can maybe justify removing. It's really difficult to justify removing an outlier, and so we rarely do that. So one thing we can do is actually take the natural log of an outlier, and that actually makes the values smaller, makes them closer together, and it reduces the effect of an outlier. Or we can run the analysis with the outlier or without the outlier, and then compare the results and see how they change. All these are perfectly fine. We can talk about it more online, but those are some tips for that. All right, pause.